This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Today's discussion centers on a seminal paper from 2016, Neural Machine Translation by Jointly Learning to Align and Translate. This work significantly advanced the field of neural machine translation. Let's begin with the core problem addressed in this research. What were the limitations of existing neural machine translation models at the time?
Existing encoder-decoder models relied on encoding the entire source sentence into a fixed-length vector. This bottleneck severely hampered performance, especially with longer sentences. The fixed-length vector couldn't adequately capture the nuances and complexities of longer sequences, leading to information loss and decreased translation accuracy. The model struggled to handle sentences longer than those seen during training.
So the core issue was the inability to effectively handle variable length sentences. How did this paper propose to overcome this limitation?
The authors introduced a novel architecture that jointly learns to align and translate. Instead of compressing everything into a single vector, their model encodes the source sentence into a sequence of vectors, each representing a part of the sentence. Crucially, the decoder then adaptively selects the most relevant vectors for predicting each target word. This attention mechanism allows the model to focus on the most pertinent parts of the source sentence for each word in the translation, regardless of sentence length.
This adaptive selection of relevant vectors is key. Can you elaborate on the mechanism used to achieve this soft search for relevant parts of the source sentence?
The decoder uses an alignment model, a feed-forward neural network, to compute weights for each annotation vector. These weights, denoted as IAge, represent the probability that the ith target word is aligned with the jth source word. The context vector used by the decoder is then a weighted sum of the annotation vectors, where the weights are these probabilities. This allows the model to softly attend to multiple parts of the source sentence simultaneously.
The paper mentions a bidirectional RNN for the encoder. What's the advantage of using a bidirectional RNN in this context?
A bidirectional RNN processes the input sequence in both forward and backward directions. This allows each annotation vector to incorporate information from both preceding and succeeding words in the source sentence. This provides a richer context for the decoder, improving the accuracy of the alignment and translation.
The paper highlights the importance of soft alignment as opposed to hard alignment. What's the distinction, and why is soft alignment preferable?
Hard alignment creates a one-to-one mapping between source and target words, which is often too restrictive for natural language translation. Soft alignment, on the other hand, allows for probabilistic relationships, enabling the model to consider multiple source words when generating a single target word. This is particularly beneficial in handling word reordering and dealing with phrases of differing lengths. The soft alignment also allows for backpropagation of the error signal, improving training efficiency.
The paper presents quantitative results using BLU score. What were the key findings regarding the performance of the proposed model compared to existing approaches?
The proposed model, RNN search, significantly outperformed the standard encoder-decoder model, especially for longer sentences. Importantly, RNN search achieved translation performance comparable to state-of-the-art phrase-based systems, even without using additional monolingual data. This demonstrated the effectiveness of the proposed approach in overcoming the limitations of fixed-length vector representations.
The qualitative analysis in the paper provides insights into the alignment produced by the model. What were the key observations from this analysis?
The visualizations of the alignment weights showed largely monotonic alignments, with strong weights along the diagonal, indicating a direct correspondence between source and target words. However, the model also exhibited non-monotonic alignments, correctly handling word reordering and capturing complex relationships between phrases. The soft alignment allowed the model to handle cases where the direct word-to-word mapping was insufficient.
The paper also discusses the model's performance on long sentences. How did the proposed model handle long sentences compared to the baseline?
The RNN search model showed significantly improved robustness to sentence length compared to the baseline encoder-decoder model. The baseline model's performance degraded dramatically with increasing sentence length, while RNN search maintained high accuracy even for very long sentences. This highlights the effectiveness of the attention mechanism in handling long-range dependencies.
The paper mentions related work in the area of learning to align. How does this work differ from previous approaches, particularly Graves' work on handwriting synthesis?
Graves' work used a mixture of Gaussian kernels for alignment, restricting the alignment to monotonic shifts. This is a significant limitation for machine translation, where non-monotonic reordering is common. The proposed model, in contrast, computes alignment weights for every source word for each target word, allowing for flexible and non-monotonic alignments.
The paper also discusses the broader context of neural networks in machine translation. How does this work differ from previous approaches that used neural networks as components within existing statistical machine translation systems?
Previous work often used neural networks as auxiliary components, providing features or rescoring candidate translations. This paper, however, presents a complete neural machine translation system where all components, including the alignment mechanism, are jointly trained. This represents a significant departure from previous approaches and demonstrates the potential of end-to-end neural models for machine translation.
What are the key takeaways from this research? What are its main contributions to the field?
The paper's main contribution is the introduction of an attention mechanism that allows neural machine translation models to effectively handle variable length sentences. This was achieved by jointly learning to align and translate using a sequence of annotation vectors and an adaptive attention mechanism. The results demonstrated significant improvements in translation accuracy, particularly for longer sentences, and achieved performance comparable to state-of-the-art phrase-based systems.
What are some of the limitations or future directions suggested by the authors?
One limitation is the computational cost associated with computing alignment weights for every source target word pair. Future work could explore more efficient alignment mechanisms. Another area for improvement is handling unknown or rare words, which is crucial for real-world applications. The authors also suggest exploring the use of larger monolingual corpora for pre-training the encoder.
This has been a very insightful discussion on a landmark paper in neural machine translation. Thank you for your expertise.